Hey, AP Chemsters, this is Mrs. Vanderlei bringing you another edition of the Blankwalle series. Today we're doing section 14.7, the reaction quotient, which is predicting the direction of change. Hopefully that you have done the chem activity in class today, that group work, where you were discussing what Q was and how things were affected if you added more products or added more reactants to the equation. How did that equilibrium system shift? And that's what this section is all about. So let's begin. What is reaction quotient? So first of all, here's our equation that we're going to assume we're going to be using here. And the reaction quotient is this. Wow, this looks a lot like that law of mass action that we have started this whole chapter off with. The difference is, unlike a Q or the equilibrium constant, that this can be measured at any point during the reaction. And what we will do with this value that we come up with is we're going to compare it with the K equilibrium. And that's going to tell us how we're going to shift the equilibrium. Is it going to shift towards more products, or is it going to shift towards more reactants? The Q can be measured in concentrations or in pressure. But like I said in letter C, the equilibrium constant is a numerical value only at equilibrium. So you only use the K for equilibrium and only has one value. However, Q can be found at any time and can be of any value. It is then used to compare it to K to determine how far the reaction has progressed. So let's see some examples down here. Let me scroll down a little bit. All right, so if a mixture contains only Q, or it's the only reactants, what does Q equal? Well, Q is usually products over reactants. So what happens if there's only reactants? We have zero products. So as you know, what is 0 divided by any number? It is 0. So if you only start off with just reactants and the reaction has not proceeded to make any products, your Q equals 0. And no matter what, it's going to be less than K. K has to be a positive number, so you know that Q is going to be less than K. What if the mixture contains only products? Well, let's check this out. So if it has only products, it means it has 0 reactants, and therefore it is equal to infinity. Well, as you know, infinity is going to be bigger than any K value possible. So at this point, if you only have products, that Q will always be greater than K. So what if the mixture all contains equilibrium constants of 1? You figure it out. Well, hopefully you figured out that once again Q equals products of reactants, and if everything is equal to 1 molar, then Q is equal to 1. Now, not knowing what K is, I don't know in this case, if example number 3, that if Q is equal to 1, is it greater than K or less than K? We don't know that. We just plugged in some numbers. Now, this part right here is going to be the really important idea for this entire section. So its Q is useful because the value of Q relative to K, so you always compare which one's bigger, Q or K, is a measure of the progress of the reaction towards equilibrium. So if Q is equal to K, what does that mean? You're at equilibrium. The reaction is going to stay where it is. It's not going to shift any of your moles from one side to the other side. If Q is greater than K, well, what does that mean? Well, the system is going to shift to the left, consuming more products and forming more reactants. And check this out. This is why. So we're back here. This is letter C. I wrote this down for letter C. So Q is greater than K. So what's going to happen? We're going to want to lower Q, so eventually we'll equal K again. Well, what's Q equal to? Products over reactants. How am I going to lower Q? How do I get this number to be a smaller number is really what's being asked. What am I going to do to products? Well, hopefully you figured out that you have to lower products. What's going to happen to your reactants? So if you lower products, you also have to increase your reactants. So if you want Q to get bigger, I'm sorry, I said that wrong. If Q is bigger than K, you want Q to get lower. I'm sorry about that. So if you want Q to get lower, you want products to go down, you want reactants to go up. So how will this shift? Well, what's going to make more reactants? Reactants are going to get bigger. You're going to shift to the left. Let me scroll back up here. You want more reactants. So you're going to shift this to the left. You want more reactants, you're going to shift it to the left. Here are your reactants, you're going to shift it to the left. Let's see this other case here. So what if Q is less than K? So now what? It says the system will shift to the right, consuming reactants and forming products so the equilibrium is reached. So let's check this out again. I'm going to scroll up a little bit more. So if Q is less than K, what do we need to do? We need to increase Q. We want to make Q bigger so that will equal K. Well, how are we going to do that? So how will this be achieved? Well, Q has to get bigger. So let's kind of look at this again. Get to know this equation right here and reason this stuff out. Let's think about it. Q needs to get bigger. So what's going to happen to P and R for Q to get bigger? What will P have to do? Get bigger or smaller? Think about it. What will R have to do to make Q get bigger? Hopefully you came to this conclusion. You want pressure, or I said that wrong, that products will go up and reactants will go down. So what way will this end up shifting? If you want more products, go towards more products. Let me scroll back up here again. If you want more products, what's going to happen? You're going to have to shift to the right. So this is when Q has to get bigger. This is when Q has to get smaller. Okay, so that is how the Q will predict how the equilibrium will shift. Let's go on to the next page. I really like this picture because it really is a good visual of what's going on here. So this is as a reaction proceeds, and notice K is right here at Q equals K. So this is your equilibrium at this point right here. And so notice as the reaction proceeds, I love this. As the reaction proceeds, look what has to happen to Q. Q is getting bigger and bigger and bigger until it eventually reaches K. What if you have way too many products? Q is going to be way up here. So what's going to happen? It has to get back down to the equilibrium constant. So it's going to decrease to get back down to this K value. So here we have different time factors. Here, look at the different concentrations. So I'm going to use these numbers. And let's check this out. Well, first of all, here's our equation. That probably been a good thing to look at. So let's check this out. So what is the value of K? Well, I just kind of told you that. See this red line here? That's the value of K, and we called it 1.5. So now what? It says solve Q at each point and state the significance. So at point 0, here's your point 0. It's at the beginning of your reaction here. So Q equals B over A. Why is that? Well, it's products over reactants. So same thing I have up here. So our products at point 0, we don't have any products. So it's going to be 0. What is our reactants? It's 1. So here we go. Here's our product 0, reactants 1, and as you know, it equals to 0. So what's happening here? Compare. Q is 0, K is 1.5. Q is less than K. So if Q is less than K, what does that mean? We need to add more products. We need to decrease the amount of the reactants. Okay, so isn't that what's going to happen here? As the reaction proceeds, look what happens. Our reactants go down, our products go up. That's exactly what needs to occur. So let's check the next one out. At point 1, here's point 1. All right, our products is 0.25. Our reactants is 0.75. Notice it's gone down. So now what? Our Q is 0.33. Look at Q. Q has gone from 0 to 0.33. Q is going up, just like this picture shows. I love this. But still compare 0.33 versus the K value of 1.5. Q is less than K. So it's the same situation as up here. If Q is less than K, you need more products, less reactants. We need to continue to shift this to the right to create more products. And notice the arrow is going up to do that. So let's check out if point 2. So at point 2, let me scroll up a little bit. Here's point 2. We have equal values, equal molarities of product and reactants. So if we have equal molarities, we have 0.5 products, 0.5 reactants, and hopefully you can do the math in your head to get 1.0. So once again, compare this to K. Is Q bigger than or less than K? Well, hopefully you figured out that Q is still less than K. So what does that mean? We still need to shift this to the right. We still need to make more products and create less reactants. So let's check this out. So if here is 0.2 and here is K, aren't we still decreasing the amount of reactants and increasing the amount of products? That's what it looks like to me. Okay, so let's check out at 0.3. At 0.3, it looks like our products have increased to 0.75. Our reactants have gone down to 0.25. And if you do your division, hopefully you don't need a calculator for this, you get 3. Oh, something's changed here, isn't it? 3 is bigger than 1.5. So what does that mean? Now Q is bigger than K. So how will this equilibrium react? Well, how are we going to make Q a smaller number? We need to decrease the numerator and increase the denominator. So you need less products and more reactants. Let's check out the graph here. So when you're up here, here's 0.3 it looks like. It looks like you have too many products and not enough reactants. Look at this. The reaction is going to run to the left. It's going to shift to the left to create more reactants to get us back down here again. And you can probably figure out at 0.4 what's going to happen here. Here we have all products and no reactants. Excuse me. And so 1 divided by 0 is infinity. So no matter what, Q is going to be bigger than K. So we need a lot less products and a lot more reactants. So checking out Q, notice Q can be a different number as the reaction proceeds, but notice we're always comparing it against the singleton value of K. It's your only value of K. And how will the reaction shift, how it will react to this changes is going to depend on if Q is less than K, it's going to shift to the right. If Q is greater than K, it's going to shift to the left. I hope that makes some sense. Let's go on to the next page. So problem 19 states, consider the reaction and its equilibrium constant. So there we have our reaction working with iodine and chlorine to make two monoiodine monochloride there. And the Kp is a kind of a big number. It favors the products for sure. It's an 81.9. Notice it's a pressure value. So here's our reaction mixture contains, and doesn't say it's at equilibrium. Notice it does not mention it is at equilibrium. It's just what are the conditions at this given point. So the pressure is 0.114 for iodine, 0.102 for chlorine, and the ICL is 0.355. Is the mixture at equilibrium? So whenever you are asked that, you got to solve for Q and see if that Q value is equal to the 81.9. So here's my Q. Notice once again, see the 2 here? I had to square the pressure of the ICL. And this is the pressure of the iodine times the pressure of the chlorine. So let's just plug in those values. Notice here the ICL is 0.355. Here is your pressure of the iodine times the pressure of your chlorine. And when you get that all together, I get, hopefully I didn't make a mistake, is 10.8. So let's compare 10.8 versus 81.9. What's happening here? Q is what? Think about it. Write it down. Q is less than K. So now what? We need to make Q bigger. How do we increase this value? How do we increase the 10.8? Well, look over here. What has to get bigger? The products or the reactants? What has to get bigger? Well, hopefully you figured out. If Q needs to get bigger, we're going to have more products, less reactants. How will it shift? That's what they're asking. What direction? Will it shift to the left or shift to the right? Well, if you want more products, you have to shift to the right. We're going to make more products. So let me shift it. So we're going to shift it to the right so we make more products. Why don't you try number 20 all by yourself? So pause this, work out the math, calculate Q, determine the shift, and see how you do. All right, this is what I got. Hopefully it's what you got. So notice I had to square the NO2, divide by 0.0311, which was my reactant. I got 0.0196. Now look at this number, compare it to 5.8 times 10 to the negative third. What's happening here? This number is bigger than the K value, so Q must get smaller. Notice that K can't shift. K can't change, Q can. So Q must get smaller. So how to get smaller? We have to decrease our numerator and increase our denominator. I guess I forgot the word R here. So how is that going to happen? If I want more reactants, it's going to shift to the left. Why don't you go ahead and we got to continue on with the next one. Talk to you soon.